Okay, so next we're going to do another, actually the last of theorem in our kind of basic introduction to graph theory. This is a theorem due to Turan. Now, Turan is another one of these very famous names that's attached to a theorem that we're passing over in our first kind of basic pass. Turan's mostly a number theorist, one of the greats in the 20th century, but he also did quite a bit of graph theory. Let me tell you a story about Turan, since well, since I have a minute, and it's a nice one. So Turan was born into a Jewish family, and he's as a result in Hungary at the time he was not able to get a good job, and rather worse, when the Nazis came to power, he was put into a labor camp. It was actually multiple times, I think, he was put into labor camps. But I imagine most people who are in labor camps are just fantasizing about escape. But Turan was thinking about mathematics. So in the labor camp where he worked, they were firing bricks, and they had so they'd have these kilns. I don't know, maybe they had 4 kilns, and then they had some storage centers for the bricks. And what happens is that they the bricks would be carried back and forth on little like railroad tracks between the kilns and the storage units. And well, to leave everything nice and flexible, what they did is they arranged. Ooh, oh, that wasn't my best edge. Okay. Sorry, this is not my best. So this would be K44. So anyway, in order to leave everything flexible, they arranged that the tracks had every kiln connected to every storage unit. But this meant that there were lots of little places where they had crossings, so where one track crossed another, and those places were quite terrible, because the bricks would tip out of the little carts they were running along these tracks, and I imagine that was bad for the people who were working there. And at any rate, and so Turan saw this and thought about graph theory. He asked a famous question about how you draw a complete bipartite graph in such a way as to minimize the number of this number of crossings. And this is known as Turan's brickyard problem, and it's still a famous unsolved problem in graph theory. Yeah, okay, so that's my quick anecdote about Turan. Let me get to today's lesson. So this is something that we do understand. This is a problem that Turan did solve, and it's really the start of extremal graph theory. So roughly speaking, extremal graph theory is sort of the following kind of problem. Suppose I have some little subgraph that I care about, and I'd like to find that in my big graph. How many edges does the big graph have to have before you'd be forced to see that little subgraph? So that's kind of our game here. And Turan answered this question for complete graphs. So I'm going to use slightly different notation. You remember we have this term independent set. So a subset of vertices is independent if there are no edges that have all of their ends in that set. So there's a kind of complementary notion that's also useful, and I'll introduce the term for it. If G is a graph, a set of vertices X, this is a clique if every pair of nodes in X is adjacent. Let me say vertices. So, in other words, a subset of vertices is a clique if and only if the graph induced on them is a complete graph. So it's it's sort of just saying you're looking at a subset of vertices that would forms a complete graph as a subgraph. Okay, so that's our notion of clique. And so Turan's question that he answered here is, well, if I give you a simple graph, say on n vertices, how many edges do you have to have before you're going to be forced to make a clique of size, say 3 or 4 or something like this? And actually, this is just a good thing for you to stop and take a moment to think about. So suppose I were to challenge you to make a graph, let's say on 100 vertices, and you want, it's got to be a simple graph, so I'm not playing with loops and parallel edges. So it's going to graph on 100 vertices and simple. And I want you to try to put as many edges as you can in this graph, but the restriction is you're not allowed to make a triangle. So you're not allowed to have a K3 subgraph. Or in our new language, you're not allowed to have a clique of size 3. So it's just worth thinking about. I mean, it's a good idea to maybe pause the video here. Why don't you pause the video and take a moment and think to yourself for a minute, how would I try to make a graph that has lots and lots of edges and but doesn't have a K3 subgraph? Okay, so if you're coming back to us or you're just sort of listening through, let me just sort of tell you the answer. Here's a way of making a graph that has no K3 subgraph and has lots of edges. So I'll take two large sets that are going to be independent, and I'll take all edges in between them. So in other words, I'm just describing a complete bipartite graph again. Right? If I give you a complete bipartite graph, then it clearly is not going to have a clique of size 3. It won't have a K3 subgraph, because if you pick up 3 vertices, well, you have to pick up 2 on the same side, and those 2 won't be adjacent. So so this graph, it can have quite a lot of edges. If you had let's count actually. Suppose n was an even number and I put n over 2 on the left and n over 2 on the right, then I'd have n squared over 4 edges, right? Because I'd have one edge for each choice of a vertex on the left and a vertex on the right. So so that's pretty good. N squared over 4 edges. The complete graph only has about n squared over 2 edges, so you've got about half the edges you could possibly have. And this is a very dense graph, but it doesn't have a K3 subgraph. And in fact, you can generalize this. So let me do. Oop. Why is that not? Oh. There we are. Suppose you wanted to make a graph that had lots of edges but did not have a K4 subgraph, or did not have a clique of size 4. Here's a thing you could do. Make 3 big independent sets and take all of the edges between them. So let's make a graph like that. Again, you can see that this graph is not going to have a K4 subgraph. It's not going to have a clique of size 4, because however you pick up 4 vertices, you'd have to pick up 2 from the same one of these blocks, and those 2 would not be adjacent. So this graph will not have a clique of size 4, and it can have quite a lot of edges. So I'm not going to bother to do the counts here, and they're getting a little bit trickier as we go. But this is a nice way to make a graph that would have lots of edges, but would not have a K4 subgraph. And it turns out that, in fact, this is the best you can do. So if you're interested in making a graph on n vertices and you want no clique of size 4 and you want to maximize the number of edges that you have, the best thing you can do is take your n vertices and split them into 3 sets of as equal size as possible, so differing by at most 1, and and then take all of the edges in between those sets and none within each set. And that's that's what Turan proved in this famous theorem. So let me get the theorem statement up here. So I'm going to be talking about a simple graph. I'm going to give it a name. So let's let G equal V comma E be simple. I'm going to tell you I've got n vertices, and now I'm going to promise you that there's no clique of size t plus 1. So if every clique of G has size at most t, then you cannot have too many edges. Then the total number of edges is going to be at most 1/2 1 minus t times times n squared. Yeah. Sorry, I was about to write some nonsense there. So let's actually let's just do the special case. We saw let's suppose n is even. So let's say n is equal to 2k, and let's take t equal 2. So here I'm picking a couple of particular parameters here, but this is back to the problem I asked you to think about. So I'll tell you that n is going to be an even number, and I'll excuse me, I'll ask for a graph that does not have a clique of size 3. So in other words, every clique has size at most 2. So you don't see any K3 subgraph. So in that case, this is telling us that the number of edges here would be at most 1/2. So here t is, oh my gosh, this is why I should sorry, there's some super nonsense there. 1 over t, 1/2 times 1 minus 1 over t times n squared. Sorry, this would be total nonsense here otherwise, because t would be well, anyway, the previous formula was wrong. This formula is now correct. So the number of edges is always at most 1/2 times 1 minus 1 over t, the quantity, times n squared. So let's plug this in for when n is 2k and t is 2. So here our number of edges would be at most 1/2 times 1 minus 1/2 times, so n here would be 2k, so I would have 4k squared. Sorry, 4. My apologies. I would have 2k quantity squared, which is 4k squared. And you can see here I get a half times a 4k squared, so this is k squared. And here the complete bipartite graph, k, k, k. This is going to be a simple graph on 2k vertices, so which is n vertices, that has no k3 subgraph. This has no clique size greater than or equal to 3. And the number of edges of this graph this is k squared. Oh, sorry about that. So that's k squared. So we're seeing that in fact, just as I promised you. So this complete bipartite graph with the same number of vertices on both sides, that is the best you can do. If you want to make a graph that has, it's a simple graph that does not have any triangle, no clique of size 3, and you want to pack as many edges in as possible, this is what you need to do. You need to take a complete bipartite graph, and you want the two sides to be as balanced as possible. So Turan's theorem is a huge generalization of this. So it works not just for K3 subgraphs or triangles. It works for any value of t. And as I'd indicated, the extreme examples here are always kind of this same form. They're looking like if you want to have all cliques of size t or smaller, then you can take t independent sets. You partition your vertex set into t blocks with equal sizes or almost equal sizes. You have all those sets be independent, and you take all of the other edges, and that's going to be the best you can do. Anyway, so that's the content of our theorem, and this is really the bread and butter of extremal graph theory. We have some structure that we're interested in finding. How many edges do we have to put in our graph before we're forced to see this structure that we want? Okay, so that's our theorem, And now let's do the proof. I think maybe we'll have to just I'm not sure what I want to do here. Maybe I just want to kind of remember this formula. So let me because I can't I can't hold on to all of this. I want to flip the page here, but let me just kind of keep that formula up in mind. So we're trying to prove that the total number of edges is less than or equal to 1/2 1 minus 1 over t times n squared. So again, G is going to be an n vertex graph. All cliques of G are going to have size at most t, and we're trying to prove this this bound. So that's our game. Now, our proof is going to be induction. That probably shouldn't be surprising to you. We love inductive proofs. It's one of our best tools. So how is this one going to go? Well, we're going to go by induction on the number of vertices. So our induction on n here, which is this is the number of vertices. Now, conceivably here, you could take the base case to be n equals 1, but actually we're going to want a slightly larger base case. So you'll sort of see why when we go to do our inductive operation, but I can tell you ahead of time, in short, what's going to go on. Our inductive operation is going to be assuming that our graph has at least t plus 1 vertices. So we're going to do an inductive step, and when we're doing that inductive step, we're going to be assuming that we have at least t plus 1 vertices in our graph. Otherwise, everything's going to break down. So because our inductive step needs us to have at least t plus 1 vertices, well, then our base case is going to have to handle all the rest. And that means that our base case is going to be all the graphs with t or fewer vertices. Right, and this is generally speaking how induction goes. So again, you've always got some base case and you've always got some inductive step, and kind of how much the base case has to handle really depends on the workings of the inductive step. If your inductive step requires your graph to have at least 50 vertices, then your base case is going to have to handle all the graphs with fewer. Right? And same thing here. So in ours, we have this parameter t that's running around, but when we get to it, you will see that the inductive step, I'm starting off making some assumption that we've got at least, that we've got a lot of vertices around, at least t plus 1 vertices. And so if that's what I'm going to do when I want to do the inductive step, my base case better handle everything smaller. So our base case here is when n is less than or equal to t. Now, when n is less than or equal to t, remember our assumption about this graph is that every clique has size at most t. Well, if n is less than or equal to t, that assumption is actually vacuous. If I give you a graph with n vertices, it can't have a clique of size larger than n, right? I mean, you can only have a clique of size n. So if n is less than or equal to t, then our graph definitely will not have a clique of size t plus 1. So here the assumption's not valid. So there's not much going on. In fact, you can just have your whole graph be a complete graph, and that's how you'd have as many edges as possible, and you certainly won't have a clique of size t plus 1, but that complete graph is going to satisfy our bound, as we'll see here, right? So again, here the number of edges in my graph, so the number of edges in the whole graph, I have a graph on n vertices. If it's the complete graph, I'm going to have n choose 2 edges. If it's not the complete graph, I'm going to have fewer. Remember, right now we're in the land of simple graphs, so there are no parallel edges or loops or anything. I'm just talking about simple graphs. So if I've got n vertices, the most edges I could have would be n choose 2. So the number of edges is less than or equal to n choose 2. And of course, this is 1/2 times n minus 1 times n. And I can write this in a funny way. I'm going to pull a factor of n out of that n minus 1, and and tack it on the end. Right, so the number of edges in my graph is going to be less than or equal to 1/2 times 1 minus 1 over n times n squared. But now you remember here, n is less than or equal to t. And that means this whole quantity is going to be less than or equal to 1/2 times 1 minus 1 over t times n squared, right? If t is greater than or equal to n, then 1 over t is less than or equal to 1 over n. So 1 minus 1 over t is going to be greater than or equal to 1 minus 1 over n. And so we get this, this inequality. So again, we are now assuming that n is less than or equal to t, and we've just observed that the number of edges in our graph is going to be less than or equal to this 1/2 1 minus 1 over t times n squared, and that's what we're trying to prove. So so this maybe looks like a bit of a tricky base case, and I guess it sort of is. It's unusual in that our base case is not just one vertex graphs or two vertex graphs or something. It's these are now graphs that can have up to t vertices, and t is a parameter that's moving around, but the structure of them is still simple. So although t is kind of a moving parameter, it's really not so tricky. Anyway, and we've done it. So there's our base case. So for the inductive step, now I can assume n is bigger than t. I mean, I shouldn't even say we may assume. I should just say for the inductive step, n is bigger than t. And again, we're assuming that this formula is holding true for any graph on on fewer vertices. So I have a graph on n vertices. It is simple. It does not have a clique of size t plus 1. And also all cliques have size at most t. And I'm trying to prove that it satisfies this this bound on the number of edges. And again, because I've said we're going by induction on the number of vertices, the thing that we know is every graph with fewer vertices satisfies this bound, right? Okay, so there we are. Now I'm going to make a another simplifying assumption. So I claim that we can freely assume that our graph has a clique of size t. Remember, our basic assumption is that there's no clique of size bigger than t. But suppose I gave you a graph that doesn't even have a clique of size t. Well, I could freely add an edge to that, and I would still have a graph that has no clique of size t plus 1 or larger, right? If you have a graph where the biggest clique is size t minus 1, I could just add an edge to it, and by adding one edge to the graph, I can't increase the size of the largest clique by more than 1. So in other words, if I gave you a graph which wasn't even tight, in the sense that you don't even see a clique of size t, all cliques have size smaller than t, I might as well just add an edge to it, and I still get a graph where all cliques have size at most t. That graph that I'm just giving to you here, that graph, if our theorem is true, it had better satisfy the formula, so it had better have at most this 1/2 times 1 minus 1 over t times n squared edges. And if that's true for this graph, it's certainly true for the graph that you get by deleting an edge, because that's just driving down the number of edges. So in other words, what we can do here is by possibly adding edges to the graph, I can assume that there is a clique of size t. Again, every time I add an edge, I'm only increasing the clique size by at most 1. So if the graph doesn't even have a clique of size t, I'll add an edge. If it still doesn't have any clique of size t, I'll add an edge. I will do that up until I get to a clique of size t, but no cliques of size larger than t. And then that's the graph that I'm going to operate with. Again, if we can prove that graph satisfies this upper bound on the number of edges, then that will be true about the original one. So this is all to say we may assume, and this is by adding edges, that that G has a clique of size T. This is a pretty common thing that we see in graph theory. You know, if you're assuming your graph, doesn't have this structure, well, usually you can assume that you can. If the basic assumption you have about your graph is that it doesn't have a certain structure, usually you can assume that your graph is kind of close to having that structure, because otherwise you can sort of do these sort of free operations. Okay, at any rate, at the moment now, we know that there's a clique of size T, and I'm going to choose one. Let's select one. Let's let choose one. So I'm going to let A be a clique of size T, and I'm going to let B be the rest of the vertices. Okay. Now, now what we're going to do is look at this picture. I'm just trying to figure out how to use my space here. Yeah, let me just get a new free page. Let's just jump ahead. Okay, so again, here A is a clique. B is the rest of the vertices. And and maybe I'll bring back the formula I'm trying to prove. We're trying to prove some upper bound on the number of edges. But let me go ahead and draw a picture here, because the picture is really where it's at. This is what's going to help us understand what's going on. Here's our set A. Again, that's T vertices and it's a clique. Here's the rest of the vertices over here, B. And again, we've split our vertices into two sets, A and B, and this gives us kind of three types of edges in the graph. There are edges with both ends in A, there are edges between A and B, and then there are edges with both ends in B, right? And what we're going to do is, well, we're trying to find an upper bound on our number of edges. What we're going to do is we're going to find bounds for those three kinds of edges. Now, I'll remind you that we've got T vertices here, and all the rest are in B. So they're n minus T over here in B. And here's where you're seeing me wanting to assume that I have a clique of size T in the graph. Sorry. Here's where you're seeing me want to have more than T vertices in the original graph. I want A and B to be both non-empty here. So just to keep everything simple, and and that would be violated if my graph had too few vertices. So this is why I needed that base case to be covering a little bit more than maybe it sometimes does. Okay, so let's think about the types of edges that we have here. Now, the graph A. Let's I don't know. Okay, let me just so. Let's think about how many edges we have in these three different groups. Right? We've got edges back and forth, edges with both ends in A, and edges with both ends in B. Now, how many edges have both ends in A? That's actually a very easy one. The subgraph A, it is a clique. It is, you have edges joining every pair of vertices in there, and I have T vertices in there, so I have T choose 2. Excuse me. I have T choose 2 edges in there, and that's equal to 1/2 times T minus 1. Okay, so that's pretty good. So I have a easy bound on the number of edges with both ends in A. Now, how about these edges between A and B? Well, I claim that every vertex in B must be not adjacent to at least one of the vertices in A. So in other words, my claim is that you cannot have a vertex that's in B that's joined to every vertex in A. It might be worth stopping to think for a moment why that's true. So why is it the case that you cannot have a vertex in B that's joined to every vertex in A? So the reason you can't have a vertex in B that's joined to every vertex in A is that would give your whole graph a clique of size t plus 1, and we're assuming you don't have one of those. So again, every vertex in B, it can't join to all the vertices in A. It can join to at most t minus 1 of those t vertices. And that's giving us a bound on the number of edges that we can have between the two graphs, right? If I give you a vertex that's in the set B, it can join to at most t minus 1 of the vertices in A. So there could be at most t minus 1 edges from A over to that vertex. And that same bound works for all n minus t of the vertices in B. So the number of edges here between A and B is going to be at most, what am I saying? T minus 1 times n minus t. Right? Again, what I'm giving you here are upper bounds. Right? The total number of edges between A and B, it's going to be less than or equal to t minus 1 times n minus t, because for every vertex in B, it joins to, every one of the n minus t vertices in B, it joins to at most t minus 1 vertices in A. Okay, so that's good. I've got a good bound on A. I've got at least a decent looking natural bound on the number of edges between A and B. But how about B? We hardly know anything about B, right? What do we know about B? All we did was we chose a clique A, and we sort of pulled it off. What do we know about B? Well, we don't know too much, but we know that it's a simple graph, and we know that it doesn't have a clique of size t plus 1, and we know that it's smaller than our original graph. So what do? We apply induction, right? So we can apply our theorem inductively to the graph B. So by induction, this total number of edges that we see with both ends in B, it's going to be what? Well, it's going to be at most 1/2 times 1 minus t times the number of vertices here, which is n minus t squared, right? So that's my bound on that guy. So again, what we've done here, we are proceeding by induction. We have used some structure to get a handle on our graph. We pulled out a clique of size t, that's our set A. The rest of the vertices form the set B. And now we've found bounds on the number of edges with both ends in A, the number that go from A to B, and the number with both ends in B. Again, number with both ends in A is easy. That's just because we're staring at a clique. The number of edges between A and B, we're getting a bound on because A is a clique of size t. Every vertex in B must be non-adjacent to at least one of those. And for B, we're just using induction. But again, now what we've done is we've found upper bounds on the number of edges of all three of those different types, and now we're just going to combine those, and that's going to be the proof of our theorem. So what we've got here is that our total number of edges is going to be at most 1/2 t times t minus 1 plus t minus 1 times n minus t plus 1/2 1 minus t times n minus t squared. Why don't I just go ahead and expand that n minus t squared? So n minus t squared is n squared minus 2nt plus t squared. Okay, now, and actually let me, sorry, now that I see that I can do this, let me maybe even a little bit more greedy here. Split this up. I mean, this is all I've done right now is written down our bound, right? We found upper bounds on the number of edges of those three types. I've written them down. I'm just going to take this t minus 1 times n minus t and expand it. So I want to write this as t times t minus 1 times n and t minus 1 times minus t. So I'm just going to take this term. In fact, look at what I'm going to do. Just drag it down here, and now I'm going to replace it by something that you'll see is obviously the same. So this is minus t times t minus 1, and then I'm going to have plus n times t minus 1. right? So I've just replaced this n minus t times t minus 1 with those two terms, and you can see that that was a valid use of the distributive rule. And now we'll just collect things and see that it works out as we want it to, or as we're claiming it does. So let's look at the terms that don't have an n. So we're kind of expecting those to go away. If you remember, the formula that we're looking for in the end is just going to have a factor of n squared. So all of those terms with no n's should kind of be going away. And let me just sort of highlight them here. So I've got a 1/2 t times t minus 1. I've got minus t times t minus 1. So together those combine to make a minus 1/2 t times t minus 1. But I've also got another term out here. You've got t squared times 1/2 times 1 minus t. Well, oh my gosh. I am so sorry. I don't know why I'm writing. I made that mistake twice here. Our inductive bound on the number of edges, the bound is the number of edges is at most 1/2 times 1 minus 1 over t times n squared. So when we apply induction, our bound is 1/2 times 1 minus 1 over t times the quantity n minus t squared. Sorry, I don't know where my head is at. 1 minus t makes no sense at all. It has to be 1 minus 1 over t. Anyway, so when you take this t squared term and multiply it by 1/2 times 1 minus 1 over t, well, just take one factor of that t squared and push it through. T times 1 minus 1 over t gives me t minus 1, right? So the upshot is that all of the terms here that I've underlined in orange are just canceling, right? What I'm left with here, this is equal to n times t minus 1 plus 1/2 1 minus 1 over t times n squared minus 1/2 times 1 minus 1 over t times 2nt. Right? So this is, again, all I've done here is I've canceled my orange terms, so I get an n times t minus 1, and then I've hopefully applied the distributive rule properly there at the end. And now let's look to see what's happening. Well, you see this, this term n times t minus 1, that's in fact canceling with this, right? When you take this t times 1 minus 1 over t, that just turns into a t minus 1. The 2 and the 1/2 cancel. So the two terms I've underlined in red here, those are just the same terms with opposite signs, and so they cancel each other. So after all the dust settles, we are left with 1/2 1 minus 1 over t times n squared. So we've proved that the number of edges in the graph is at most 1/2 times 1 minus 1 over t times n squared, and that was our target, and that completes the proof, and that completes our lesson.